Welcome back, folks. Here we're looking at section 10.2, the unit circle, sine and cosine, and this is part one of what is split into two separate lessons. So they'll be labeled that way when you go to look at both the guided notes page that goes along with it and the videos in YouTube. Okay, so we're going to start today by talking about special right triangles, and I know what you're thinking. Mr. Vass, aren't all right triangles special? Well, yes, they are. So maybe we should more appropriately call these extra special right triangles. So these extra special right triangles that we're talking about today are the 45-45-90, otherwise known as the isosceles right triangle. And there's some information, little kind of hint up here about what we're going to use with the a special relationship we're going to use for the 45-45-90. The other special right triangle is the 30-60-90, and here's the relationships we need to know for those. So I think what I'm going to do here is I'm first going to look at this example one. It says complete the table of values for each triangle. I'll go slowly through the first example and then quicker through the other two. So what I have here in this first example is a 30-60-90 right triangle. I have the origin down here labeled as point O, so that angle O is 30 degrees. I have a point A labeled up here in the upper right hand side of the triangle. I have a horizontal distance of X and a vertical distance of Y. So first thing we'll do, take a look at, is the measure of angle O in radians. Well, I have 30 degrees, and I remember from a previous lesson that if I can multiply by pi over 180 degrees, that's the conversion factor to go from degrees to radians, and that gives me a result of pi over 6. Now, folks, I'm going to be honest with you. After working with radian angle measures for a couple days, you shouldn't need to do that conversion factor every time. They should start to come naturally to the point where you just know that 30 degrees is pi over 6 radians. Okay, so how do I come up with the x and y values for this triangle? Well, I start by looking at the fact that the hypotenuse has a length of 1. If I go up to my special relationship that I'm highlighting up here for the 30-60-90 right triangle, the hypotenuse is 2 times the short leg. Okay, so what the heck's the short leg? Well, that's this one across from the 30-degree angle. That must mean that the side across from the other angle, the 60-degree angle, is the long leg. And I use that long and short terminology up here in these highlighted formulas. So if the hypotenuse is 2 times the short leg, that means the short leg is half the hypotenuse. So y, the short leg, is going to be 1/2. Now for the long leg, I have to do a little more work. The relationship up here is that the long leg equals √3 times the short leg. So that means I have to do √3 times 1/2, which we would write as √3 over 2. So those are the distances x and y from the figure. Now, what is the cosine of theta? Well, the cosine of theta, the cosine of O, if I recall, the cosine of any angle is the adjacent leg over the hypotenuse. So the adjacent leg, which is the long leg, x, over the hypotenuse, 1, is going to give me the value x over 1. And for this figure, that's √3 over 2. For the sine of angle O, it's going to be opposite over the opposite leg divided by the hypotenuse. So that's going to be y divided by 1, or in this case, 1/2. Last thing I want to do here is show you the xy pair for point O. The x distance is √3 over 2, and that y distance is 1/2. Okay, what I'm going to do now is I'm going to pause the video and kind of fill out the rest of this table for you, and then just highlight some of the key features after I'm done. Okay, folks, got the rest of the table filled out for you. Just a couple things I want to highlight here. For this triangle in the middle, it's a 45-45-90 right triangle, also known as the isosceles right triangle. The angle measure there is pi over 4 radians, and the x value is 1 divided by √2. Well, how do we get that? Well, the formula for a 45, 45, 90 right triangle is hypotenuse equals root 2 times leg. Well, if the hypotenuse equals root 2 times leg, the leg equals the hypotenuse divided by root 2. That's where 1 divided by root 2 comes from. A pretty standard practice in mathematics is to rationalize the denominator there. So we'll do that by multiplying this by root 2 over root 2. So we don't change the value, we just change how it looks. And that gives us a result, a familiar result of root 2 over 2. Okay, so that value is copied down in the rest of these boxes, but I just wanted to show you where that comes from. So you'll notice that I have an x and y value of root 2 over 2, cosine and sine of root 2 over 2, and then the ordered pair right here, x comma y. Last triangle we'll take a look at here is the 30, 60, 90. This is really just a kind of rotated image of the one we were looking at first. We've got an angle of pi over 3, x and y values of 1/2 and root 3 over 2, then the associated cosine and sine ratios in ordered pair. What I want to do right now is highlight something that's very important. I want you to take a look at the values in this row and see how they compare with the x coordinates here. Hopefully you'll recognize that they're identical. And then look at the values in this row. Hopefully you recognize that they're identical with those values. So what this means in terms of right triangle trigonometry and its connection to the unit circle is the following. Our xy values, x comma y, our x comma y values for an ordered pair of a point on the unit circle are equal to cosine of the central angle, comma sine of the central angle. I can't emphasize how important that is, folks. We're going to be using that for the rest of the semester. You need to know that an xy pair on a circle has the coordinates of cosine theta, comma sine theta. Critically important. Pause the video right now and just do whatever you need to do. Run a couple laps, do some push-ups, whatever you need to do to get fired up to memorize that and understand it for the rest of the year. Okay, let's move on to example 2. And we have a note here that says the unit circle is a circle with a radius of 1. That's something we've talked about in class, but we're going to use that to our advantage when we're looking at problems like those in example 2 here. So it says draw each angle on the unit circle and then determine the sine and cosine of the angles. Okay, so we got a couple that deal in degrees and then we'll move into radians. First one we'll look at is 270 degrees. I will draw it in standard position. 270 degrees is 90 degrees times 3, so it looks like this. And the x and y coordinates of this point right here on the unit circle are 0, negative 1. If you recall what I said a second ago, x comma y is cosine theta comma sine theta. So my cosine of 270 is 0 degrees, and my sine of 270 is negative 1. Remember that connection, folks. X coordinate is cosine, y coordinate is sine. Okay, let's look at another angle, 135 degrees. For this angle, I'll go ahead and draw it in standard position. Now 135 is halfway between 90 and 180, so it's right about there. Now, how does the 45, 45, 90 triangle relate to this? Well, here's our 135 degree angle, but the 45 degree angle is really right here. So what we kind of have here is a 45, 45, 90 triangle off to the left-hand side in quadrant number 2. We'll use that to our advantage later, but for right now, I want to go ahead and identify the x and y coordinates of this point right here. The x coordinate is going to be negative. It's going to be negative root 2 over 2. Remember, this is our friend, the 45, 45, 90. The y coordinate is going to be root 2 over 2. How do we get those values? Well, if I'm working with a unit circle, the radius is 1, and I can use properties of special right triangles to figure out those x and y values. So I have a sine ratio in this case, which is the y coordinate. It's √2/2. Notice that it's a positive value. And a cosine ratio, which is negative √2/2. Important for you to be able to keep the positive and negative values straight. We're in quadrant 2, so the x values are negative, the y values are positive. Okay, let's move on to an angle that's measured in radians, and this one is 2 pi over 3. So how do we draw 2 pi over 3? Well, we start by trying to get the screen not to jump around on us. We start by drawing the initial side of the angle in the standard position. And then what I like to do here is I like to think of, this is 0 and this is pi. 1/2 a rotation gives me pi radians. And this is 2 pi over 3. So if I take this 1/2 rotation and I split it into thirds, 1/3, 2/3, that would give me 3/3. 2/3 is what I need for 2 pi over 3 radians. So that angle right there is 2 pi over 3. Now, how does this relate back to our special right triangles? Well, this side over here, this is a 60-degree angle right here. So I know I have my hypotenuse of 1. My short leg, which is here, my x value is going to be -1/2. That's my x coordinate. My y coordinate is going to be √3/2. And if you're not sure where those values come from, go back and look at the table at the top of the page to see how we came up with those values. Okay, so cosine is the x coordinate, -1/2. And sine of theta is the y coordinate, or √3/2. Again, we're in quadrant 2, so the x value is going to be negative, the y value is going to be positive. Moving on, let's look at theta equals 7 pi over 6. I'm going to have my initial side drawn in standard position, and now I have to look at 7 pi over 6. Well, I'm going to use the same idea I had before. That's 0, this is pi, and if I want to split that into 6 chunks, 1, 2, 3, 4, 5, 6, that's great, but now I need a 7th chunk to give me that 7 pi over 6. So there's my value of 7 pi over 6. Now, how do our special right triangles fit into this one? Well, this little angle right here, try and make that blue for you folks. This little triangle right here, that angle is 30 degrees. Okay, so that's going to help me identify the coordinates of this point out here on the unit circle. That short leg is 1/2, but it's negative because I'm going down from the x-axis. So that's a y coordinate of -1/2. The x coordinate is going to be -√3/2. And again, that's all from the work we did previously at the top of the page. I just have to keep track of what quadrant I'm in and which values are positive, which values are negative. Cosine is the x coordinate, -√3/2. Sine is the y coordinate, -1/2. All right, folks, what I'd really like you to do for these next two is pause the video and see if you can't do these on your own. And then I'm going to go ahead and fill in all the work for them, pause the video myself while I do that. I want you to check your work. All right, folks, there's the results for part E and F of this example. We looked at 5 pi over 3 and 7 pi over 4, two angles that are both in quadrant number 4. So my y coordinates are negative. You can see that because my sine ratios are both negative. My x coordinates are positive, so both cosine ratios are positive. We're pushing upwards of 15 minutes here, so I'm going to go ahead and shut this video down. I'm going to do another part of this for the back side of the notes page.